This is the last problem of this slide. A shell and tube heat exchanger with 2 shell passes and 8 tube passes is used to heat ethyl alcohol. For ethyl alcohol, Cp is equal to 2670 joule per kg degree Celsius in the tubes from 25 degrees Celsius to 70 degrees Celsius at a rate of 2.1 kilogram per second. The heating is to be done by water. Cp is equal to 4190 joule per kilogram degree Celsius that enters the shell at 95 degrees Celsius and leaves at 60 degrees Celsius. So we have all these four data: temperature 25, 70, 95, 60. So we can easily calculate log mean temperature difference from this information. If the overall heat transfer coefficient is 800 watt per meter square degree Celsius, determine the heat transfer surface area of the heat exchanger using these two different methods. First one is the LMTD method and the next one is the NTU method. So this is the figure of this problem having all this information. Water enters at 95 degrees Celsius and leaves at 60 degrees Celsius, and alcohol enters at 25 degrees Celsius, 2.1 kilojoule per kilogram per second, and leaves at 70 degrees Celsius. And this is a two shell, one shell and other shell, two shell pass and 8 tube passes. Okay, so this is a two shell pass and 8 tube passes heat exchanger. So there is the solution analysis. Number A, the LMTD method. The temperature differences between the two fluids at the two ends of the heat exchangers are del T1 is equal to Th in minus Tc out. So 95 degrees Celsius minus 70 degrees Celsius, that means 25 degrees Celsius. Like that, del T2 is equal to Th out minus Tc in, that means 60 degrees Celsius minus 25 degrees Celsius, 35 degrees Celsius. So we have del T1 and del T2 respectively 25 degrees Celsius and 35 degrees Celsius. So we can calculate the logarithmic mean temperature difference very easily. So del TLM CF is equal to, CF means cross flow, counter flow, is equal to del T1 minus del T2 divided by ln del T1 by del T2. So 25 minus 35 divided by ln 25 by 35. So the value of the logarithmic mean temperature difference for counterflow is 29.7 degrees Celsius. P is equal to T2 minus T1 by T1 minus T1, 70 minus 25, 95 minus 25, that means 0.64, and R is equal to T2 minus T1 by T1 minus T1, so 95 minus 60 and 70 minus 25. This is T2. Okay, printing mistake. So the value of P is 0.64 and R is 0.78, and from these two value we can find the value of F, which is 0.93. The rate of heat transfer is determined from this equation. Q dot is m dot c Cpc Tc out minus Tc in. We have all this value. M dot c is 2.1 kilogram per second. Cpc is 2.67 kilojoule per kilogram degree Celsius. Tc out means 70 degrees Celsius and Tc in minus 25 degrees Celsius is equal to 252.3 kilowatt. This is the value of Q dot. The surface area of heat transfer is Q dot is equal to US del T Lm. So AS means Q dot divided by U del T Lm into F. So Q means 252.3 kilowatt, U means 0.8 kilowatt per meter square degree Celsius, F means 0.93 fouling factor, and del T Lm or logarithmic mean temperature difference is 29.7 degrees Celsius. So the value of Q dot is 11.4 meter square. This is the solution of number A, that means the LMTD method. The next method is the effectiveness NTU method. The rate of heat transfer is Q dot is equal to m dot c Cpc into Tc out minus Tc in. So we have all this value. After calculation, the value of Q dot is 252.3 kilowatt. The mass flow rate of the hot fluid is Q dot is equal to m dot h Cps Th in minus Th out. That means m dot h is equal to Q dot divided by Cps Th in minus Th out. We have all this value. So the value of m dot h is 1.72 kilogram per second. So we know the value of CPH, CPC, and the mass flow rate for hot fluid as well as cold fluid. So we can determine the value of CH and CC. So the value of CH is m dot s into CPH, so 7.21 kilowatt per degree Celsius, and the value of CC is m dot c into CPC, 5.61 kilowatt per degree Celsius. Therefore, C mean is equal to CC, 5.61 watt per degree Celsius, and C is equal to C mean divided by C max, that means 5.61 divided by 7.21. So this is the value of C, 0.78. Then the maximum heat transfer rate becomes Q dot max is equal to C mean into TH in minus TC in. We have all this value. After calculation, we can find the value of Q dot max is 392.7 kilowatt. So the effectiveness of this heat transfer is epsilon is equal to Q by Q max. The value of Q is 252.3 and the value of Q max is 392.7. So the value of effectiveness 0.64. The NTU of this heat transfer corresponding to this emissivity and C is equal to 0.78 is determined from figure 13.26. 2B NTU is equal to 1.7. Then the surface area of heat transfer is determined to be this equation NTU is equal to UAS divided by C mean. So AS is equal to NTU multiply C mean divided by U. The value of NTU is 1.7. C mean means 5.61 kilowatt per degree Celsius and U means 0.8 kilowatt per meter square degree Celsius. So the value of AS or surface area is 11.9 meter square. The small difference between the two results is due to the reading error of the chart. So the two process or two methods, first one is the LMTD method and the next one is the effectiveness NTU method. So this is the solution of this problem. Our last topic, selection of heat exchangers. An engineer going through catalogs of heat exchanger manufacturers will be overwhelmed by the type of number of readily available of the shelf heat exchangers. The proper selection depends on several factors: heat transfer rate, cost, procurement, maintenance, and power. So three types of cost: pumping power, size and weight, type, materials, miscellaneous, that means leak tight, safety and reliability, as well as quickness.